Hello students, welcome to this session. Today we are going to learn the real gases and their behavior. The state of gas is represented by its volume V, pressure P and temperature T. These equations or these three quantities are not independent of each other. If any two of these entities are fixed, the third one automatically becomes fixed. For a given mass of the gas, we can establish a relation between them. This is done empirically on the basis of experimental observations or through kinetic theory. This relation is called as equation of state of the gas or simply gas equation. The equation of state of the gas must be such that it is able to represent the behavior of gas correctly for all values P, V and T. So this is the equation of state. Now what is the ideal gas? As we know, the equation PV is equal to RT for ideal gas. An ideal gas obeys Boyle's and Charles' law for all values of volume, pressure and temperature. On the basis of the above laws, for 1 gram mole of gas, that is the ideal gas, we obtain the equation of state, that is PV is equal to RT, where R is the constant of gas and which is universal. It is same for all ideal gases and its value is R is equal to 2 calorie per mole per Kelvin, or we can write 8.31 joule per mole per Kelvin. Equation PV is equal to RT is also called the ideal gas equation. It is assumed that an ideal gas behaves according to this equation under all conditions. The ideal gas equation is based upon the following two assumptions. 1. Gas molecules are mere point masses and they do not occupy the space. And the second one assumption is the gas molecules do not exert attractive or repulsive forces on each other. It means that is they do not interact and the energy of the gas is only due to the motion of its molecule, that is kinetic. So there is no potential energy in the gas. From the ideal gas equation, we find that for a given mass of the gas at a fixed temperature, the product of pressure and volume remains constant. So that is PV is equal to constant, and this is Boyle's law. Thus, keeping the temperature constant, if pressure is changed, the volume of the gas adjusts itself such that the product PV is constant for all values of the pressures. A graph of PV against P will be a straight line parallel to the pressure axis. It is implied that an ideal gas does not liquefy as in liquid and solid states. the molecule attracts with each other. In the deviation from the perfect gas equation, here the P pressure on x-axis, while on the y-axis we are taking the PV. So this dashed line is referred for ideal gas for corresponding this 0 degree centigrade, 200 degree centigrade. Even Boyle's law, the gas found that the real gases obey the gas law only in special condition of high temperature and low pressure. To test the behavior of gas, the graph is plotted for P against PV at various but fixed temperatures like 0 degree centigrade and 200 degree centigrade. So these are called isothermal curves. If the gas obeys equation, the PV graph should be rectangular parabola. Experimentally, it was found to happen only seldom. To study the behavior of real gases, Regnault performed a set of experiments. He studied the behavior of gases like nitrogen, hydrogen, carbon dioxide in the temperature range from 0 degree centigrade to 100 degree centigrade and the pressure up to 30 atmosphere. In another set of experiments, the Amagat studied the behavior of nitrogen, hydrogen and carbon dioxide up to pressure of 3000 atmosphere. To represent the behavior of these gases, he plotted the graph with the product PV along the coordinate axis against the pressure P taken along the abscissa. So he draw the behavior. Some deviation takes place for nitrogen gas. So this deviation gives the behavior of gas. It means it liquefies, or what happens at the when you are increasing the pressure in atmospheric and we are drawing the P versus PV. So small deviation takes place here. From these two slides, these gases were obeying Boyle's law, that is PV is equal to constant. The product PV should have been constant for all values of P at a given temperature, and the PV versus P graph should have been a straight line parallel to the P-axis. But experimentally it was not found true. The graph are inclined to the P-axis. For hydrogen, the product PV increases with increase in pressure on this slide. On the other hand, for nitrogen gas, with increase in P, the product PV first decreases. This PV is going to decrease for this value and this value, acquires a minimum value and then increase as in case of H2. The minimum value of PV here and this one depends upon the temperature of the gas. In case carbon dioxide, the graphs PV versus P were found typical. Below 30 degrees centigrade, part of these curve is parallel to the PV axis, indicating that through P remains constant, the volume changes. This situation corresponds to the condensation of vapors. On increasing the temperature, the curvature of the curves goes on reducing. Yeah. And the point of minimum value of PV goes on reading from the origin, this side. If we plot a curve joining these minimum values of PV, we get approximately a parabola, this dashed line. In fact, all the gases exhibit a behavior like the carbon dioxide gas. The only difference is the H2 shows this type of behaviors at very low temperatures. Here, this behavior of carbon dioxide is more illustrative compared to nitrogen. The study indicates that the gases which liquefies at relatively higher temperatures exhibit more deviation from the Boyle's law. For hydrogen, it was observed that the value of PV initially decreases and then increases with the P. The gases which liquefies at relatively high temperatures that exhibits more deviation from Boyle's law. For hydrogen, it was observed that the value of PV decreases with increase in P when the temperatures are below minus 175 degrees centigrade. At a particular temperature, the PV becomes parallel to the pressure axis. This temperature depends upon the gas and is called Boyle's temperature for the gas, Boyle temperature for the gas. At this temperature, the gas obeys Boyle's law. Such experiments were also performed by Andrews, Holborns, Owens, etc. to study the behavior of real gases at various temperatures and pressures. Andrews' experiment provided detailed and better understanding of the behavior of gases. On the basis of these studies, van der Waals make the corrected gas equation known as van der Waals equation. The conclusion of the above experiments are shown here through PV versus P. The graph represents in general the behavior of all the gases and make the conclusion that none of the real gases is ideal all the gases are imperfect as they do not obey the gas equation. The easily liquefying gases such as carbon dioxide, ammonia, that exhibits more deviation from the gas equation. The permanent gases such as nitrogen, hydrogen, oxygen do not exhibit much deviation. From equation PV is equal to RT at normal temperature and normal pressure. At lower temperature, these gases also exhibit a large deviation from the ideal gas behavior. For every gas, there is a particular temperature called the Boyle's temperature, at which the product PV remains constant, almost constant, with a variation in pressure. When the pressures are very high, the product increases. Below the boil temperature, with increase in pressure, the product PV first decreases, acquires a minimum value, and then start increasing. Above the Boyle's temperature, with increase in pressure, the product PV first decreases, acquires a minimum value, and then starts increases. Above the Boyle's temperature, with increase in pressure, the product PV also increases. Boil temperature for nitrogen is 50 degrees centigrade. For hydrogen, it is minus 175 degrees centigrade. For helium, it is minus 250 degrees centigrade. It is why helium and hydrogen gases exhibit increase in product PV with pressure at normal temperature. While for N2, a first decreases and then increases. This explains the graphs for the figure first slide and second slide. So this is the behavior of real gases with their state of equation of state and ideal gas. In next session, we discuss viral equation of state and the Andrews experiment. On the basis of such behavior of gases, Andrews performed experimentation series on the carbon dioxide and draw the various isothermals. He obtained the values of volume corresponding to various pressure, keeping the temperature constant. And then he draw the curve between P and V at constant temperature. That curve is called as isothermal curve. The isothermal curves obtained by Andrews between 10 degrees centigrade and 50 degrees centigrade and studied the behavior of gas. So till the Andrews experiment, we will stop here. Thank you for watching this video. Thank you.